In this video, we're going to take a look at complex ions and the equilibrium that governs their formation, as well as how we deal with combining K values in coupled reactions. So for example, if we have two equilibrium reactions that are happening simultaneously or subsequently, how can we combine those reactions to create a single net reaction and also understand the equilibrium of those? A big theme again here is going to be that we have big K means equilibrium. That can apply to a huge range of reaction classes, and that subscript, in this case Kf being our new one, is going to refer to the equilibrium of a specific reaction, the formation of a complex ion here. As mentioned, we have a new equilibrium constant which is called Kf, the formation constant, or the equilibrium constant for the formation of a complex ion. And in general, here's going to be the case. We have a metal ion, and ligands are attaching to this metal ion, and it's going to make a larger ion that can act as a single cation. Most often a cation, though sometimes an anion. Here, because the reaction is metal ion and ligands are becoming a complex ion, all are aqueous, and we just have products over reactants. It's still equilibrium. Specifically, we may have the following thing. We may have a copper-2 metal, which has 4 ammonia NH3 ligands, and it's becoming this copper tetraammonia complex. And because this is a chemical reaction, we have a Kf that's products over reactants. Note the 4 on NH3 becomes an exponent. And here's the value of this constant, 5.6 times 10 to the 11, and these tend to be large and positive, indicating a favorable formation of this complex ion. This is what this would look like, right? We have the copper 2 plus in the center, and it's 4 ammonias that are attaching to the central copper. We'll talk more about these quite a bit in the next few chapters. This one has a coordination number of 4. It makes square planar, but we could have something, an octahedral is very common for these complex ions, and this would be an octahedral iron complex ion. As we mentioned, the formation constants tend to be very large and positive, and here's a breakdown of different complex ions that are formed just from their parts. We have a central metal, and we have a certain number of ligands that attach to that to make this complex ion. The formation constant in all these cases is very large and positive, indicating favorability for the complex ion. Large numbers, right, and they can range from pretty large to extremely large. Okay, so let's look at an example problem. So what if we mix together iron nitrate with sodium cyanate? We want to know what are the concentrations of the iron, the cyanate, and this complex ion that will form at equilibrium, and we have the Kf for this. Now, first let's find the molarities, because we know the molarities of the iron and the cyanate that are going into solution. We know that there's no complex to start, but we do know that those amounts of the two parts that make up the complex ion are known here in the beginning, right? We also know that we have a really large Kf, and this is so large that we can assume that it's going to be nearly all product, right? There may be a limiting reactant here, right? So it may not eliminate both reactants equivalently, but we're going to assume that the reaction is going to go to completion. And when we do that, we can see the following, right? We start with 0.003 molar iron 2 plus. We start with 0.070. We start with 0.070 molar cyanate and none of the complex ion. They will shift to the right as far as they can, consuming all of the iron and leaving pretty much no iron and then the other following concentrations. And we pretty much have the concentrations for the remaining cyanate and the amount of the iron complex that's formed. But note that because this is equilibrium, the iron 2 can't be truly equal to 0. And so while we've sort of assumed this pseudo-zero to it for now, note that the K expression still has to hold, right? And while these are the equilibrium constants for the other two species, we don't yet know the iron. We just plug them back in and we obtain the iron 2 concentration, which we see is extremely, extremely small, yet still we do need to have a non-zero concentration for Kf to be true. Otherwise, 0 in the denominator, it would be infinity. Okay, so what about a question about how does complex ion formation affect solubility? And this is a really good question because we've learned about solubility. We know that when we have silver chloride in solution, it will form the silver chloride solid, right? And so when we have this, right, what happens if we have a complex ion that may form here? Here, if we're investigating in ammonia, both reactions are happening simultaneously. And this is to say that we have the solid silver chloride that's dissolving according to its KSP. This is that expression and the corresponding K value for KSP. And we also have the complex ion forming, which is this expression, where we have the silver plus and the two ammonias that are forming this complex ion, and we have the following Kf here as well. So this is a question, right? Like, if we have the presence of ammonia, do we think that there will be more or less solid silver chloride able to dissolve when this complex ion has the potential to form? So at this point, I would recommend you go ahead and pause the video and see if you can predict this, right? When we have the potential to form this complex ion because ammonia is around, will more or less silver chloride dissolve? In other words, is the solubility going to be greater or less? All right, hopefully you've come up with an answer, and the answer is that it should increase the solubility. Note that the formation of the complex ion is actually drawing silver plus out of solution, and if we draw silver plus out of solution, then the first reaction is going to want to shift to the right, which represents more solid dissolving. All right, as a bit of a concept checking question, go ahead and pause the video here and try this one. Let's rank the solubility of silver iodide in the following three solutions from smallest to largest. We have Ki, or an iodide solution, we have NH3, an ammonia solution, and we have pure water. And note that we have two relevant K values above. All right, hopefully you've gotten a chance to choose what you think the smallest to largest solubility should be here. The largest solubility is going to be in the ammonia, right? Because when we have the formation of this ammonia complex, it again is going to draw silver out of solution, which basically makes more room for silver iodide to be able to dissolve. The least soluble is the Ki, because in this case, we already have iodide in solution. That's less space available for silver iodide to dissolve. Remember from solubility that the KSP is really much more about the dissociated particles than it is about the solid itself. What about calculating this, right? How can we actually calculate the solubility of a solid within something like this? And we'll go ahead and look at a model problem first. So the question is, what's the solubility of silver chloride in this ammonia solution? And note that we have the following two reactions, right? We have the solubility of AgCl and we have the formation of this complex ion. Now, we can just put these together, right? Let's just add the two together. And if we do this, we get the following net reaction. This is literally the two reactions on the right, just added one plus the other. Note that we actually have the silver plus cancel out as it appears in the reactants on the Kf and the products on KSP. Now we can get the following here, right? The breakdown of our ice table. And this is a little bit tricky to figure out, I suppose, but note that the solubility is always going to be the amount of silver chloride that dissociates X is what we're setting up here. We start with an initial amount of NH3, and we start with none of the products, and it's just setting up an ice table with that in mind. X here is going to actually be the solubility of the silver chloride in this 0.1 molar ammonia solution. And the K net here, the K that corresponds to this reaction, it's not KSP and it's not KF, but it's the two of them multiplied by one another. We've added the two individual reactions. K net, the K that corresponds to that net reaction, is going to be the two Ks multiplied by one another. And this is a really important characteristic of equilibrium constants. When we add reactions, we multiply their K values. But here, while it is a bit of a tricky setup and it may seem different, remember that just like in acids and bases, when we have the K and the K value and we've set up the ice table correctly, it's all sort of the same thing, right? We know what products over reactants is for this K net. We have an expression with our X's in place that we've gotten from our ice table, and we can just go ahead and solve as we have the value of K. We take the square root of both sides here, don't have to solve a quadratic or anything like that, and we end up with a solubility as 4.5 times 10 to the negative 3. And that is actually the solubility of the silver chloride in this NH3 solution. How does this compare to pure water? Well, think about what we learned previously, right? How does the formation of a complex ion make the solubility change? And the answer is that the solubility should increase, and it sure enough does, right? The solubility in pure water is on the order of 10 to the negative 5, and here we have it on the order of 10 to the negative 3.